As Tobias was saying, the topic of this talk is fracture and delamination in packaging material. And this is my summary of my PhD defense that I did in 2019. And we did, the topic was on the packaging material of Tetra Pak, packaging solution. And a lot of the work that I will present here, the material was delivered from Tetra Pak and Skill and Lesson here from the company, and a few of other colleagues of him has heavily contributed and collaborated during this project or during this work. Yeah, so packages, what is so special about it? So I would say if I want to motivate why we study a bit more about package, I can say that if you cannot easily open a package, so the product itself might be quite nice and good, you might not buy that particular product. It's important to look into packages, and especially how user-friendly is the opening of those packages. So to look at that, first, let's try to look at how a package, or what are the different layers, or what are the different materials in a package. So that to the right, you can see some of the manufacturing procedure, and to the left, I can say this is an exemplary package from Tetra Pak. The top one is polymer up to there, high density, low density polymers. That's not laminated, that's like single layer material. But it can also be, if you look at the paper board that you can see in a simple package, outside it looks paper board, but there are multiple layers inside. That means that a simple package would have injection molded polymer and will have laminate of multiple layers. So each of those layers has certain purpose to be in the package. For example, some for example, the aluminum is a barrier to the light, and they have this polymer coating in the package that allows for any protection against the air in the environment. So if we want to look into the openability of package, so we have to design such packages which are user-friendly for opening. So here are some of the examples of exemplary solution of opening. So all of you probably you are familiar with, this is cap opening. This is some different sort of cap opening. And for example, here you have tearing opening, which you have to tear the package to open it. This could be a perforated straw hole where you can open and complete the product through that. So these are different opening solutions available in the package. And if you want to develop a package with easy opening solution, so what could be like, this is the product development so at the beginning of any development, or when you approach this problem or designing a new solution, so you might not have enough knowledge that how this design or how this particular combination of material might be effective as for the user to, when they open it, they get a better user experience. So there are two approaches. Basically, you can do prototyping and test it with customers, how it looks, or test it with different sort of experimental test, or you can do finite element simulation, right? So there are two approaches there. But this is time consuming, so and it's as well as resource is intensive. So the natural way of product development, or in terms of this product actually goes towards doing finite element simulation. So basically it goes like there are designs, they are tested, and based on the performance, they are redesigned. And if we want to, as I said, want to do it quite rapidly, the natural way is to go to finite element simulation of those packages. But then the geometry of the package that you choose is maybe the minor part of it when you want to do the finite element simulation. The most important part is how do you define the material property? How do you define the material, the continuum property, what's the fracture or damage property of this material? So that after the simulation, when the results are available, what sort of torque or force, for example, needed to open the package, So for the simulation, those results are reliable. So that's important. So for that, there are a lot of mechanical testing needs to be done. And from those testing, you will get, for example, this is the hardening property of material. There are other fracture properties that is needed to be included in the material model. And that's put back into the geometry of the package, right? So these are few of them. So one of the study that we did is this multi-layer laminates in the packages. So this is one layer of aluminum foil, and then there is LDP, low-density polyethylene or ethylene, that is a polymer. And this particular study will look into that if there is a defect in the interface of these laminates, and these packages are loaded in certain type of forces, how this defect can propagate, or what is the forces, or what's the nature of propagating those defects. So we have done finite element simulation study, theoretical. So the credit goes a lot to Eskil Andreasson here from Tetra Pak. So some of those work has been done in his earlier work. So we have validated, and it seems like the model we proposed for the finite element simulation looks quite reasonably, and thus could be used further into simulation of package development. There was another study to look into the interface property of the laminate. So if we have so I can maybe jump to that. For example, if here we say there are two layers, this is aluminum, and this is a LDP polymer layer. And if you want to know that how this property, what's the lamination property between those two layers, so there are many tests that we can do. So one of the tests that we used here is peeling. So there are two layers, one layer is fixed, the other layer is peeled. Similar that you peel fruits, and so you can peel from one to another. And once you have that response, it is possible to define using cohesive element. Probably that goes into the detail, but certain finite element and certain property in those elements to optimize for what is the interface properties that between those two layers. Because it's super important that you model that correctly, the interface property, to really trust a simulation of a package opening, for example, theory that you are doing using finite element simulation. So it's important that that trust is there, and for that the testing is necessary. So here is one study that we did that field test, and that was not sufficient. We have certain experimental input or a certain actually interface property input, and certain measurement that we get from directly from the experiment, and based on those results, we have created an artificial or trained an artificial neural network and use that one to back predict the more optimized property of that interface. So you can see the different steps that's involved during this optimization procedure. So this is basically the exploration. You have heard a lot in other experiments. This is the using design of experiments. So you explore the space of your variable, and then so here it's obtaining the acquisition of data and training, and eventually optimizing it for the property that can best optimize or represent the behavior in the finite element simulation. So here it was necessary to link Abacus together with MATLAB, and some sort of scripting goes into that. I have also developed a MATLAB application where different parameters will be tuned in, given that you have the experimental result of peeling at different angles. It is possible to optimize for the material parameters that you can use back into the simulation. So this is a validation of that, which was quite promising when we look at how well they match, or that was satisfactory enough in terms of force displacement and something called rope rotation. And there are additional parameters. So this is for field. So there are other MATLAB applications that I was developing in my PhD to optimize the hardening parameter of the material. That's also quite important. The continuity part of the material. So then there was a study on tearing. So that's definitely one mode of package opening. So we looked at that. We looked at what's the force, what the fracture surface looks like, and what's the deflection of tearing angle. So this was purely an experimental study. And based on that, we have identified that what could be the tearing force for different combination of material at different orientation. That's there. Then for cap opening, it's shear mode of failure. So we looked at the fracture of this polymer. Here it's low density polyethylene. And we have proposed certain geometry and some geometry correction factors that could be used together to identify some material property that's key for the financial simulation of those packages. So that's the summary we have. I have done a lot of mechanical testing, theoretical analysis, inverse analysis, and then finally financial simulation and validation. So what's the continuation? So I work a lot with failure of material. So interestingly, we could kind of spin off this Profile Plus or MD3S project. So there are two more projects right now. I'm leading one from KKS and another from Vinova, and both of them are looking into failure of materials. The project with Vinova is mostly automobile or metal forming. And there is another project that we are working together with Tetra, sort of continuing the same work that I did for PhD in 2019. So that's all. So thank you.